Hello. Today we are going to discuss a WKB approximation method application. I mean, by using this WKB approximation solution, we can find eigenvalues of potential well. Okay, potential well with two vertical walls. So these walls, so this looking like this. These are the two energy levels. So here we are applying WKB approximation method. So important condition here is the potential energy is varying very slowly. So this is, for example, this is our potential energy. This is a slowly varying potential. These are the two vertical parts. So here we assume, for example, E greater than V of x for all values of x. Then the WKB solution is like this. Phi of x is equal to c divided by root of p of x momentum, because last class in place of uh, p of x I use gamma of x, right? Gamma of x I used last class. So this is the general solution of WKB approximation method. If you don't know this solution, how we get the solution, please watch previous video, class number 1. This is class number 2. So in general, we have to make this solution, this linear combination. Here the plus or minus is there, plus or minus, that indicate the wave function is going to forward and backward directions. Okay, so after hitting these walls, so this is the linear combination of this wave function, where this pi of x is 1 divided by h cross integral 0 to x p of x dx, right? So this is our the solution. So we need to apply boundary condition. So if you look at here, this is x axis, this is y axis. On y axis potential energy, this is the axis. This is x equal to 0, x equal to 0, first boundary condition. This is x equal to a, the second boundary condition. So now simply we need to put this boundary condition in our solutions. These are our solutions, right? Then you will easily get these are the two different solutions, right? So after arranging these solutions, this C1 and C2, the exponential terms, so we can use, we can write this type of solution. So C1 psi pi of x plus C2 cos pi of x. So this is our first boundary condition. If you use this first boundary, this is our measure equation. Okay, this is our measure equation. Use this equation. So this is our first boundary condition. X equal to 0, at x equal to 0. Okay, the wave function is equal to 0, right? Then c equal to 0. Here if you put the 0 here, then sine 0 plus cos 0, this one is going to be 0. Then only remaining term is the cos 0 is 1, c2 equal to 0. We already familiar this type of boundary condition applications. This is very easy. Simply put this two boundary condition. Okay, x equal to 0, x equal to a in this solution. What are the two boundary conditions? The first boundary condition is psi of x equal to 0 at x equal to a. Second boundary condition, psi of x equal to 0, x equal to e. This is 0, this is 0, this is a two boundary conditions. The next second boundary condition, this is our second boundary condition. This is our second boundary condition. A function equal to 0 at x equal to a. So our equation is initially after putting c2 is equal to 0 here, then we have this equation, right? Psi of x equal to 1 divided by root of momentum in terms of position dependent c1 psi pi of x, right? Because c2 equal to 0, this is our equation. Now you can apply secondary boundary condition on this equation. So here the 0, because of wave function 0, in place of x I am using psi only, c1 psi pi of a, sine pi of a equal to 0. So for if you consider this one theta, sine theta is equal to 0. When it is happen, every n pi cases sine theta equal to 0, right? So theta is equal to n pi. So which is why I'm using here the pi of a. This pi is depends on a equal to n pi. Simply sine theta equal to 0. So theta equal to n pi. So n equal to 1, 2, 3, 4. Pi of a equal to n pi. So pi of a equal to n pi 1, 2, 3, and so on. So here the boundary condition 0 to a, right? Boundary condition or 0 to a. So then that equal to the n pi. The wave function is equal to the, we already know the equation. Pi of x is equal to 1 divided by h cross integral p of x dx, right? So simply use this equation. It's better to write here. This is our so how I got this equation from here to here. So if you use this equation, pi of x equal to 1 divided by h cross integral p of x dx, right? So this is a right here. Simply use pi of a here, then put this n pi value here. That is, use boundary condition. So to boundary condition x equal to 0, x equal to a, right? So which is why I got integral 0 to a p of x dx equal to n pi h cross. So remember this one. Sommerfeld quantization condition also to this one, right? Okay. So integral. So here the momentum, we know that momentum, classical momentum root of 2me minus v of x n pi h cross. So where the e is unknown of each n, the integral can be done by analytically, and an equation e will be found, or we can find e numerically. If e equal to 0 inside the wall, then courses. So for example, if p equal to 0 now, then you'll get n pi. We integrate this thing, so equal to the n pi h cross divided by 2me. So this is our exact solution by using WKB approximation method.